Okay, ma'am.
Good afternoon, students. Today I'm going to start the new chapter. So, in the last class, I have started module 4 test execution. And in this module, we have three main topics: test execution, process framework, planning, and monitoring the process. But here they have specified only two chapters, 17 and 20. Only two chapters are not there. Two more chapters are there. For test execution, it is chapter 17, and for planning and monitoring the process, it is chapter 20. But for process framework, there are two chapters, chapter 3 and chapter 4. Chapter 3 is the basic principles, and chapter 4 is the extension of that basic principle, and that chapter is um, ಟೆಸ್ಟ್ ಅಂಡ್ ಅನಾಲಿಸಿಸ್ ಆಕ್ಟಿವಿಟೀಸ್ ವಿತ್ ಇನ್ ಎ ಸಾಫ್ಟ್ವೇರ್ ಪ್ರಾಸೆಸ್. ನೋಡ್ಕೊಳ್ಳಿ, ಎಲ್ಲರೂ ಕೇಳಿಸ್ಕೊತಿದ್ದೀರಲ್ಲ. ಸೊ ಇನ್ ಮಾಡ್ಯೂಲ್ 4 there are three main topics: test execution, process framework, planning and monitoring the process. But here they have mentioned only two chapters, chapter 17 for test execution and chapter 20 for planning and monitoring the process. But for process framework, two more chapters are there from the same textbook, that is chapter number 3 and chapter number 4. ಅರ್ಥ ಆಯ್ತಲ್ಲ ಗೌರವ್, ನಿಖಿಲ್ and Misbah? Two more chapters here to study for process framework. Chapter 3 is basic principles and chapter 4 is test and analysis activities within a software process. So first I'll start with the chapter 3 basic principles. Then afterwards I will go to chapter 4. Okay. So that is the new chapter that I'm going to start today. That is the basic principles of software process or testing and analysis process. So in this chapter, you're going to study about the six main basic principles for analysis and testing. So before moving on to the basic principles, we'll see why do we require the basic principles and what are those afterwards. So in this chapter, you're going to study about the basic principles. That is, you're understanding the basic principles underlying A&T technologies, or A&T techniques is nothing but analysis and testing techniques. And next, you're going to uh, grasp the motivations and applicability of these six main principles in your analysis and testing process. So first we'll see the what are the basic principles and why do we require that. So mature engineering disciplines are characterized by the basic principles. Understood? Mature engineering disciplines are characterized by basic principles, and these basic principles provide a rationale for defining, selecting and applying the testing and methods. So why do we require these basic principles? Because these basic principles provides a rationale for defining, selecting and applying the techniques and methods, and they are the valid behind a single technique over a time span. And because many of the techniques will come and go, but these basic principles will reside. Okay. So the analysis and testing, it's a common practice, right? uh, when we starting from the beginning, the analysis and testing is the basic, or that it's a common practice. And the analysis and testing activities were for a long time based on the common sense and individual skills. So before developing the automated analysis and testing principles, where these where this activity, analysis and testing activity, was there for a longer time, or it was there from a long time, and this analysis and testing activity was based on the common sense and the individual skills. So if we consider the many individuals who are involved in the testing, then each individual is having his own testing skill, and hence the analysis and testing is different for different individuals. Why? Because each individual or each human being who involved in testing has own testing skill. So analysis and testing principles are divided into two main categories. One is called as the partition skill, but that cannot be used. So that these can be used in the normal system analysis and testing phases or testing process. So in this chapter, you are going to study about six main analysis and testing principles, and those are divided into general engineering principles and specific analysis and testing principles. Okay, so the basic principles are the analysis and testing principles are divided into two main categories. Those are general engineering principles and specific analysis and testing principles. So in general engineering principles, there are three techniques exist. One is called as the partition, second one is the visibility, and third one is the feedback. These are the three principles in the general engineering category. And sensitivity, redundancy, and restrictions, these comes under the specific analysis and testing principles. Understood? So total we have six basic principles. What are those? Partition, visibility, feedback, sensitivity, redundancy, and restriction. So together we have six basic principles, and these are categorized under general engineering principles and specific analysis and testing principles. It is partition, visibility, feedback categorized under general engineering principles. Sensitivity, redundancy, and restrictions are categorized under specific analysis and testing principles. We'll see these basic principles in detail one by one. So first we'll start with the sensitivity. So what is sensitivity? Why do we require that basic principle? As we know that in the system development, when the humans are involved in the design of the system or design of the software or testing of the software, there exists the human errors, right? Because human developers makes the errors and they produce the faults in the software. Okay, once the human developers makes the errors in designing and development, and these leads to the faults in the software. And once the fault exists in the developed software, that may lead to the failure of the software or failure of the system. But the faulty software may not fail on every execution. Let us consider that you people have developed one software and there exists a fault in the developed software. If there is a fault in the software, then it leads to the failure of the software. But this failure may not exist continuously. For some of the input combination, the software may fail. Okay, but it is not the case that that software is always failed. Okay, that is not the case, and hence the sensitivity principle says that better to fail every time than sometimes. Okay, so this is the main sensitivity principle. Excuse me. This sensitivity principle says that better to fail every time than sometimes. Why this is very important? Why the sensitivity has said like this? Sensitivity says that better to fail every time than sometimes. Why we are saying like this? Because if you consider the cost of detecting and repairing the software fault. So when you have developed the software, so what you are going to do, you have to detect the faults in the developed software. Once the faults are detected, what is the next step? You have to repair those faults, right? Detection of the faults and repairing those faults in the developed software. If the fault is detected immediately, means on the flies, or we can say that it is a syntactic check in the design phase itself. Means during the design phase itself, if you detect the fault immediately, then the cost of the correction is very, very small. Okay, that is the case. One first case is if we are detecting the fault immediately, then the cost of the correction is very, very less, or we can say it is very, very small. And here uh, the the fact the line between the fault prevention and fault detection is blurred, means there is no separate line exist in the fault detection and the correction. When the fault is detected immediately, or when the fault is detected in the during the design phase itself, then the detection and correction of those fault is the cost of that is very, very small, and it is almost negligible, we can say. But if the detection of the fault is postponed to some other phases, for example, if you consider, if the fault is detected uh, in the unit testing, okay, the fault is detected during the unit testing, then also the cost is relatively small, and it is somewhat more when compared to the previous stage. So in the previous stage, what happens? The fault is detected immediately. But if the fault is not detected immediately, then we are if the fault is detected during the unit testing phase, then also the cost is somewhat smaller when small, but it is somewhat larger when compared to the previous case. For example, if you consider the fault is detected at the integration level, or if it is the fault is detected during the integration testing, then the cost correction is more, or we require more cost, or it is costlier, because it is already at the integration stage. Means integration testing means once the all the independent models that are developed which are integrated together, then we are checking the system for faults. If the faults are identified during that time, or if the faults are detected during the integration testing, then what happens? The cost for correction of the faults is much larger, or we require more cost for correcting the errors. And the next case is if the fault is detected during the acceptance testing or during the system testing, then the cost is very, very large. Okay, then the cost is very, very large. So if the fault is detected immediately, the cost is very, very small. As the we are gone through the different phases of system development, and when the faults are detected during the system testing or during the acceptance testing, then the correction of those faults are very, very costlier, or we require more cost for correcting those errors. And the cost is still larger when the faults are detected by the customers in the field. Means once the software developed by you people, if you have delivered that software to the customers, and when the customers started using that and they started detecting the faults, then correction of such faults are very, very, very costly. Yeah. And hence this one is given, hence this sentence, that is better to fail every time than sometimes it's instead of uh, detecting the faults by the customers, if we detected the faults at the earlier stages itself, then correcting those faults is very, the cost of correcting those faults is very, very less. But if the faults are corrected during the system testing or during the acceptance testing, the cost is more, and even it is still more when the customers they started detecting the faults when the software is delivered to the customers and they started using it. Okay, once the customers started using this, if they are experiencing the failure of the system, or if the customers are detecting the faults, then correcting the such faults is very, very costlier. And hence we have to detect the errors at the earlier stages of the system development, then the cost will be minimum. So for that we have to go for a different testing criteria. So for that we are considering the consistency. Consistency means what, I'll explain first. Okay, so here we are to check the consistency. Consistency means whenever we are applying the different test cases and we are checking the operation of the developed system or working of the developed system, that the system should be in a working condition for different test cases that we enter, or if we are testing the developed software on different test suits, then it should give the correct result. And then we say that the system is consistent, means the system is not faced any failures, then we say that the system is consistent. Here we need to use the test selection criteria works better if every selected test provides the same result. Means what, if we are using the different set of test cases, all the test cases should lead to the same output result, then we say that the system is consistent or the software is consistent. So if the system or the developed software or the program fails for one of the selected test, then it should fail for all of them, then we say that the system is reliable. Okay, it's a reliability criteria. So means if the system fails for one test, then it has to fail for all the such selected test cases. Or if the system is successful, or if the system provides the correct result, then it should give the correct results for different test cases. And then we say that the system is consistent and reliable. So here for that, to check that, we can make use of the deadlock analysis, runtime deadlock analysis. So all of you know what is a deadlock, and then how the deadlocks are detected and corrected. You have studied in the operating system as well as you have studied in the DBMS, right? And here we are checking the system deadlock for the different programs. We can say we are checking the deadlock condition on the different machines. Suppose uh, if we are checking the deadlock analysis on a single machine which is independent, then analyzing that particular program for the deadlock on one machine, then it should have the deadlock situation when we are running the same software on different machines. So checking or analyzing the deadlock situation in a single machine is not efficient. So because when the deadlock occurs, when more than one system is trying to get the resources uh, con- uh, trying to get the resources parallelly, then the deadlock occurs. Why? Because if one system is holding that resource and it is asking for another resource, where another resource is held by a different machine, then each machine is waiting for the resource to release by other machine, then the deadlock situation occurs. Right. So to check the deadlock condition, or to check whether the developed software pass through the deadlock situation, then you have to check that software by running on different machines or with a different system configuration, because running that on a single machine is not efficient. So if you are running on a single system, then if the program, then the deadlock is analyzed on one machine, then it deadlocks on every machine, right? Or if we say that if the um, on one system, if there is no deadlock occurs, but if we are trying that software on another machine, then there is a chance that the deadlock may occur in that particular system. And hence, to check or to perform the deadlock analysis, we have to run the developed software on different system configurations. Okay, in this way we can avoid the deadlock situation. And the sensitivity principle says that we should try to make the faults easier to detect by making them cause failure more often. Means what? So here the sensitivity says that we should try to make the faults easier to detect. So because when more and more faults are detected, we can solve those faults, or we can correct those faults so that the system becomes efficient. So hence we have to use the test cases or the test selection criteria such that more and more faults can be detected and those faults can be corrected. So here the sensitivity principle can be applied in three main ways. One is at the design level, and one is at the analysis and testing level, and the other one is at the environmental level. So here we are applying the testing criteria or sensitivity principle at the design level, and at the analysis and testing level, and at the environmental level. Applying the sensitivity principle at the design level means we are changing the way in which the program fails. Means whenever we are designing the software, or whenever we are designing the uh, program, or when we are in the design phase, we have to apply the sensitivity criteria, and we have to detect and correct the faults. That is applying the sensitivity principle at the design level. And second one is applying the sensitivity at the analysis and uh, testing level. Means here we are using the different testing techniques so that more and more faults can be detected, and detected faults can be corrected. That is at the analysis and testing level. And third one is testing at the environmental level. So here we are choosing the technique that reduces the impact of the external factors on the results. So here environmental level, because whenever the developed software or the system is going to be installed at different places, then the external place factors, for example humidity or the temperature, etc., will affect the system performance. So then the system may lead to the failure. So we have to design the system in such a way that the external factors should not affect the system performance or system operation. So these are the sensitivity parameters we are considering, or the sensitivity principle we are applying at the design level, analysis and testing level, and at the environmental level. So this is about the applying the sensitivity. So far we have discussed the applying the sensitivity principle to the design and code. And next we'll consider the uh, applying it for the deadlock situation that I already explained, right? Applying the sensitivity for deadlock detection and analyzing it. So to detect the deadlock, so first we have to run the system on run the program on different system configuration or different system environments. Then we have to analyze the deadlock, whether the deadlock will occur or not. If the deadlock occur, how we have to solve that deadlock situation, that we have to consider. Okay, so this is about the sensitivity. Next we'll move on to the redundancy. So what is a redundancy? Then how we are applying this redundancy principle? So redundancy is the opposite of the independence. So independent is different and the redundancy is different. So the redundancy is just opposite of the independence. If one part of the software artifact, for example, if you consider the software artifact or the software different phases of software development, such as the designing or developing or implementing the software, etc. If one part of the software artifact constrains the content of another, then they are not entirely independent. Because see here, if you consider the specification phase, and with the help of the specification you are designing the system or software. With the design, with the help of the design, the developers are implementing the software, right? So here all are dependent on each other, they are not independent. Because in order to implement the program, the implementers or the developers need the design of that particular software, or if you consider the system, and to design that we need the specification. So they are not entirely independent, they are all dependent on each other. And if they are independent, then we have to check the redundancy, or it is possible to check them for the redundancy as well as the consistency. So when we are performing the redundancy checking, this increases the capabilities of catching the specific faults early in the software development stages, and once the faults are detected and that can be corrected so that the system will be working in an efficient manner. So redundancy checks can increase the capabilities of catching the specific faults early or more efficiently. So that is very, very important. So here, the concept of redundancy is taken from the information theory. So in communication or in the networking area, how we are checking the redundancy? Redundancy can be introduced into the messages. So that you have studied in the computer networks, right? What is redundant network or redundant messages or not? So here we are applying the redundancy into the messages in the form of error detecting and error correcting codes. Okay, so if your developed system uh, is ready to detect the errors, then we say that the system is redundant. So it should successfully detect the errors and correct the errors. And in the case of messages, when we are transmitting the message from sender to the receiver, there we are using the error correcting and detecting codes. And those detecting and correcting codes should detect the errors if any errors occurs during the transmission, and they have, once the errors are detected, those errors should be corrected. Then we say that that particular code is redundant. Understood? What is redundant? Okay. But in case of the software testing and analysis, we are detecting the faults that could be lead to the difference between the expected output and the obtained output. Okay. So if the expected output and the obtained output are same, then we say that the system is redundant. Otherwise, the system is not redundant. Okay. In the case of message transmission, we are mainly concentrating on correction, detection and correction of the errors during the message transmission. But in case of software development or in case of software testing and analysis, we'll say that we'll identify the faults or detect the faults, and we're correcting those faults so that the expected output and the obtained output are same. If the obtained output and the expected output are same, then we say that the developed software or the system is redundant. And here we can exploit the redundancy with the help of the static and dynamic checking. So here the static type checking is redundant with respect to dynamic type checking, but it can reveal many type mismatch earlier and more efficiently. Okay, when we are considering the static type checking and dynamic type checking, static type checking is more redundant when compared to the dynamic type checking, because it detect more mismatches during the earlier stage and more efficiently it detects those mismatches. Okay, and the next one is validation of requirement specification is redundant with respect to the validation of the final software, because see here, in the during the first phase of the software development, we are collecting the requirements, and once the requirements are collected, then what is the final phase is implementing the system for the collected specifications. So then if we validate or if we compare the collected requirements with the implemented software, if the software gives the output which is expected according to the specification, or we are getting the output according to the requirement specification, then we say that the software is redundant. So here we are validating the requirement specification along with the implemented software. If they are not redundant, means if the software is giving different output that is not meeting the requirement specification, then we have to detect the errors earlier, and those errors should be detected in an efficient manner. And next one is testing and proof of properties are redundant, but they are often used together to increase the confidence. Okay. So testing and proof of properties, this is the another method we are using to check the redundancy of the system. Both that is testing and proof, they are used together and to increase the confidence of the system development team. Okay. So here testing and proof of properties are used together to increase the confidence. And here the checkable redundancy is not limited to the source code. Means we are not only checking the redundancy with the code, but it is also checked or also introduced by the programming language designers. Means during the design phase also we are checking the redundancy of the system. Understood? Any doubt in this redundancy? Okay. So first one is the sensitivity, second one is the redundancy, and third one is the restriction. We'll see this first because these three, sensitivity, redundancy, and the partition belongs to the general principles, right? The sensitivity, redundancy, and restriction belongs to the specific analysis and design principles. So sensitivity I completed, redundancy is over, and the third one is the third basic principle is the restriction. When there are no acceptable ways to check the property, then one can change the problem by checking a different, more restrictive property, or by limiting the check to a similar, more restrictive class of programs. Means here we can use the different restriction methods or the restriction strategies in order to check the implement or in order to find the faults in the implemented software. And here, when we are using the suitable restrictions, these restrictions can reduce the complex problems or unsolvable or hard problems to a solvable or simpler problems. So to do that, we have to make use of a suitable restriction strategies. And let us consider the this one. A weaker specification may be easier to check. It is it is in general we say that to show that pointers are not used correctly, but the simple Java requirement that pointers are initialized before use is simple to enforce. This is one example. Or if you consider before using the variables, you have to declare those variables first. Anyway, you have done the programming using C, right? Or in data structure also you have done the programming, right? So before using any variables, what is the first step? First step is you need to declare those variables, right? If you're not declaring and simply using it, then it may leads to the errors or faults of the program. So that then here we have to put the restriction that whenever you are using the variables, the restriction is you have to initialize those variables at the first stage itself. That is the restriction, right? That is the suitable restriction. And when we are including the suitable restriction at different places of the program, then we can minimize or avoid the program failures or the software failures. And second one is here we have the weaker specification and the stronger specification. In the first case, it is impossible to show that the pointers are used correctly. And in the second case, that is the stronger specification, it is impossible to show that type errors do not occur at runtime in a dynamically typed language, but statically typed languages impose the stronger restrictions that are easily checkable. So here we are imposing the stronger and the weaker restrictions. So in the case of dynamically typed languages, we can assure that the type errors do not occur at the runtime or during the dynamic linking. And but in the case of the statically typed languages, we have to impose the restrictions that are easily checkable. So this is about the restriction. And next we'll move on to the fourth property, that is the partition. So partition belongs to the general basic principle. So partition means basically it is a divide and conquer. Or partition is also known as divide and conquer. So divide and conquer is a general engineering principle. So what we are going to do here? Here, first we are dividing the complex problems into sub-problems and then solving those sub-problems independently. That is called as divide and conquer. It is nothing but partition. Partition means what? Dividing the complex problem into a smaller subsystem. Or if you consider the entire project is divided into smaller modules, and each module is treated independently, and each module is designed and implemented independently. Once it is done, at the last stage or at the final stage, all the independent modules are combined or integrated together, and that will result in a larger system, and that is called as the divide and conquer. Understood? Here in the divide and conquer, the larger or the complex system, or if you consider the entire project, that entire project is divided into number of different smaller modules, and each module is treated independently, and each module is designed and developed independently. Once everything is done, finally we are integrating or combining all the independent modules, and that leads to a single larger system or into a entire project. Okay, so that is the case, and that is called as divide and conquer. And here, this partition method or the divide and conquer can be applied both at the process level or at the technique level. So, at the process level means we are dividing the complex activities into a set of simple activities, and each activity is solved independently, or each activity is handled independently. Understood? Applying the partition at the process level, that is the first thing, and second one is applying the process at the technique level. Process level means we are dividing the complex activities into set of simple activities, and each activities can be solved independently or can be handled independently. And next one is at the technique or at the uh, second one is at the technique level, right? So here we are using the some static analysis techniques that follow the modular structure of the software system to divide an analysis problem into smaller steps. So in the first case, we are dividing the complex activity into smaller activities. That is in the case of process partitioning. And in the technique partitioning, what we are doing, we are dividing an analysis problem into simpler steps or smaller steps, and each step is analyzed independently. So these are the two types. Understood? Partition is applied at the process level and at the technique level. And many static analysis techniques construct the model of the system first and then analyze the model. Okay, so many static analysis technique, what they will do, first construct the system and then they analyze the constructed system. Understood? And here we are dividing the overall analysis into two subtasks. First one is simplifying the system to make the proof of the desired properties, and then prove the property with respect to the simplified model. So as I said, here we are using we are using the many static analysis techniques. So in the static analysis techniques, what we are doing, we are constructing the system model first, then we are analyzing. So construction is the first phase, then analyzing is the second phase. So here what we will do, we'll divide the entire analysis into two tasks or two sub steps. First we are simplifying the system, and then we are proving the property with respect to the simplified model. So these are the two methods we are using in the static analysis. Okay, and hard testing and verification problems can be handled by suitably partitioning the input space. So here we to check the system, we are partitioning the input space both at the structural level and at the functional level. So what happens at the structural level and functional level, we'll see. So functional testing means those functional testings are derived from the specifications, whereas in the structural testing is derived from the program structures. So here we are considering both the structural and functional test selection criteria to identify the suitable partitions of the code are the specifications. Specification belongs to the functional testing, and the second one is the criteria identify suitable partition of code. Code means it is a program structure that applies the structural testing criteria. For the specification, we'll say that it is a functional testing. If you consider the structure of the program or the code, then it is a structural testing. So here we are considering both structural and functional test selection criteria to identify the suitable partitions of the code or the specifications. Then the verification techniques for the input space according to the specific characteristics, and grouping those characteristics or grouping them according to the homogeneous data together and determining the partitions. So here we are performing the verification techniques on the input space according to the specific characteristics, are grouping homogeneous together data together and determining the partitions. So this is about the partition restriction I completed. And the fifth one is the visibility. So what is visibility? Visibility is means the ability to measure the progress or status against the goals. Here the goals are given, then we have to measure the progress or the status against the given goals. Okay, so for the any systems you can consider or any software you can consider, the goals are given and the progress of the system development you have to compare with the given goals. So hence the visibility means the ability to measure the progress or status against the goals. Here we have two types of visibility. One is called as the schedule visibility, and second one is the quality visibility. So schedule visibility says that are we ahead or behind the schedule? Means if you consider the software development process and you are preparing the plan, and in the plan you are telling that in the 2 months you are going to complete the design phase. So in 2 months you are completing the design phase, and so once the design phase is completed, you are checking that whether that design you completed in 2 months or not. So that is the scheduled visibility. And quality visibility means you are checking the quality, does the quality meet our objectives. Means so the objectives or the goals are given, and you have designed the system or you have developed the system, then you are comparing the quality of that system with the specified objectives or the specified goals. Then you, when you are comparing, then if both matches, then say that it is it is what it, you can say that we are experiencing the quality visibility. If not, then we say that it is not satisfying the quality visibility. Okay, we have two types of visibility: schedule visibility and quality visibility. And simply the visibility means the ability to measure the progress or status against the goals. For example, X visibility is equal to ability to judge how we are doing on X. Okay, for example, we have considered the scheduled visibility and the quality visibility. And the visibility involves setting goals that can be assessed at each stage of development. So in each stage of software development, if you consider the requirement specification, design, development, design, then implementation and testing. So at each stage, we are setting the goals. And once each stage is completed, we are comparing the progress with the goals that we have set. If both are matches, then we say that visibility is there. If not, then we have to reframe it. Okay, So here we are setting the goals at each stage of the software development or system development. Then we have to check whether we are meeting those goals or not. So the main challenge here we are facing is the early assessment. For example, assessing the specifications and design with respect to the product quality. So here our product quality means we expect some quality from the developed product, but comparing that product quality during the specification phase and the design phase is very difficult, because just at the specification phase or the design phase we cannot compare or we cannot expect what the quality we are expecting at the end stage. That is the biggest challenge we are facing in the visibility. And visibility is also related to the observability. So then what is observability? The observability is the ability to extract useful information from a software artifact. So observability means we are extracting the useful information from the software artifact. Artifact means it includes each stage of development. So getting the useful information from the specification phase, from the design phase and the implementation phase, it leads to the observability. Okay, observability means the ability to extract the useful information from each intermediate stage of system development. Here we can use a variety of simple techniques to improve the observability. So, for example, choosing a simple or standard internal data format to facilitate the unit testing, or we can go for the HTTP or SMTP messages, which are based on the exchange of simple textual commands. So there we can observe there we can check the observability. Okay, or the variant of observability is through the use of simple text encoding techniques. There we can directly see the data structures what we have used, either of the whatever the text we have written, whether they are in the human readable form or not, or whether they are in the editable form or not, that we can easily check through the observability. Okay, so this is about the visibility. What is visibility? There are two forms of visibility. Visibility is the ability to measure the progress or status against the goals, and we have two types of visibility: scheduled visibility and quality visibility. The last topic of this basic principle is the feedback. So what is feedback? So it is another engineering principle that applies to analysis and testing process, and feedback applies both to the process and to the individual techniques. So feedback, getting the information or getting the feedback from the end users, are getting the feedback from the testing team, are getting the feedback from the development team. Okay, so it is nothing but what getting the useful information from the end users, or from the testing team, or from the development team. And here, whenever the customers or the testers are giving the feedback, or whenever the testers are testing the system, they are making use of, or with the help of the checklist, the testing team is checking the developed system. Okay, then how the checklists are constructed, or how the checklists are built? The checklists are built from the past experience. Okay, the checklists are built from the past experience, or the checklists are built on the basis of errors revealed in the past. Okay, next, error taxonomies can help in building better test selection criteria, because number of different error exist. Based on the type of error occurred, we can categorize those errors into different categories and or different classes. Then we can identify each class of error, then that can help in getting the feedback. And the design guidelines can avoid the common pitfalls. So design guidelines means whenever the design team is designing the system, The set of guidelines are given, and all the developers or the designers should follow those guidelines in designing the system. So if all the human beings or the persons who involved in designing can follow these guidelines, then we can avoid the pitfalls. Okay. So feedback is nothing but collecting the information about the operation of the system from the end users, or from the customers, or from the testing team, or from the developed team. So to do that, the testing team is making the checklists, or they are using the taxonomies, or the design guidelines are used in order to avoid the common pitfalls. So this is about the feedback. And so far you have studied six different principles. One is the sensitivity, redundancy, and restrictions. These three comes under the specific analysis and testing principles. And partition, visibility, and feedback, these three comes under general principles. Okay, so these are the six main principles that you have studied, and these are playing a very important role in analysis and testing the system. And these principles can be used to understand the advantages and limits of different approaches and compare the different techniques. So this is about the chapter basic principles. Okay, mainly we are concentrated on six main basic principles in this chapter, and this completes the chapter. And in the next class I'm going to start the new chapter, that is the chapter number 4, test and analysis activities within a software process. Any doubt? Yes, Mispa, Gaurav, or Nikhil, any doubt? No? Then, if you have no doubt, then I'll end my class. Okay, then I'll end my class.